Hello, everyone.
Hello, everyone. Thank you for joining today. Hello, David.
Hey, can you hear me today in one go?
Yeah,
Awesome.
yeah,
Awesome.
yeah. I see people coming in. Uh, yeah, again, if you need something from me for breakout rooms and anything like that, I'm here to support.
Awesome. Yeah, I think like yesterday would be perfect. Yeah.
Yeah, okay. Yeah, perfect. Uh,
I hope I didn't scare the other 50 participants yesterday.
no, I don't think so. I think people enjoyed it actually. I still have to go through the evaluation survey, but it looked like people found it very useful, so
That's
that's
good
good.
to hear. That's very nice.
Yeah, yeah. Okay, I just made you co-host, so whenever you want, yeah, I see that more and more people are coming in, so I guess, yeah,
Maybe give it 1 minute because I think
yeah, yeah,
the topic we start today with is probably the most important one, and also
okay,
given that a lot of people asked questions about
yeah,
overfitting, uh, I don't want to. Yeah, I want to make sure everyone that's going to
yeah.
join gets this bit. Okay. Uh, I think we just have to start at some point, right? So,
Yeah.
yeah, let me just start by sharing my screen. Because today we will be covering, first of all, model quality and model selection, but also to give you a little bit of a teaser for what we will be doing the rest of today. We will have a lot smaller, and then close the theory part with also talking about ensemble methods, which is a very small extension of what we have already covered either today or yesterday. Um, because I want to have a lot of time for you to work on the larger project, we will have one large theory block of both consisting both of model quality and decision trees. And then in the first exercise or the first part of this project, we can combine the decision tree part with the model quality and selection. That means that we will probably take a small break in between the two presentations, and afterwards, after the both bits of theory, we'll move to the exercises. So just prepare yourself a little bit for a lot of theory right now. Um, and I think if you take something away from this course from both days, I think this bit uh, I think is the most important because uh, yeah, algorithm information you can easily find in either documentation or somewhere on the web. But model quality and selection basically holds for any kind of machine learning project. Um, and yeah, this part really makes sure you actually generate something that is useful in the end. Because, for example, if you would do a machine learning project and you start having a nice data set and then just build a model and that's it, and someone asks you, can I actually trust your model? Does it generate trustworthy predictions? Yeah, how do you actually know that? For example, if you need to predict whether someone yeah, is going to react aggressively on a certain medicine, you need to be very sure. So you don't want to just do some kind of coin flip. So you need to make sure your model is actually better than a coin flip, and that is what this bit is about. Um, yep. So when we're talking about measuring accuracy or by quality, we are actually checking how close predicted values of our model, so y values meaning target, are close to the actual target values in the historical data. Um, so for regression, we have already covered this, how you can determine the error. So what you can do is just look at the residual sum of squares, calculate this R2, but that's just one metric you can use for regression. There are actually, so this one is typically used for linear regression, but there are also a lot of different metrics, um, which are actually also used quite often. So the residual sum of squares is actually something we have already discussed, but just to recap and also explain a little bit the notation here. Again, y means the value of the target of observation I, and then here we have y hat is the prediction of that ith observation. So this is really the difference between these two gives you the error of your prediction of the ith observation. Typically, we always square the error and then take the sum of all different observations that we have. And this results, like we discussed yesterday, in the residual sum of squares. One that's also commonly used is not just the totals. It is basically a sum. We also look at the average. So again, there's a slightly different notation here because it's also good to know that there are different notations for the same thing. A predicted value can also be denoted with f of x, and f here is again with a hat, meaning this is f of x is basically the same as this y hat. So this is again a predicted value, the difference of the predicted value and the actual value squared, but instead of just looking at the sum, we average the value. This metric is called the mean squared error. This is a commonly used one. So also good to typically, if you do like a linear regression, you calculate this R2, and then additionally you also calculate the residual sum of squares separately and also the mean squared error separately, and just report on all these metrics to give feeling for there are in certain cases you're dealing with maybe data with a very large magnitude. So you can think of data that's in the magnitude of maybe a million, and then a difference of 10,000 might be small, relatively small in your case, and maybe not so significant. But if you look at your mean absolute mean error, you actually see that it will be very large, because if you are 10,000, you have 10,000 error, you do 10,000 squared, which is already a lot, and then it can give you a weird feeling of your model prediction uh, performance. So what you in those cases could do look at the you take the value, the absolute value of that, and then sum those percentages to get an average percentage here. This is, I have never used this in practice, but I have seen other projects use this, especially with large magnitude data. Similarly, to the mean squared error, instead of taking the square, you can also take the absolute value. So in this case, we don't do the square, but we replace squaring the error with taking the absolute value, and again we average that absolute value. So my recommendation, if you do a regression project, because these are typically only related for regression, is just calculate them all and try to see which one works better for your context. That's something I cannot give you beforehand which one works better. Um, but I would always report on all of these metrics because they're not difficult. So these were all performance indicators for regression models. Then the question is, can we actually also use these kind of metrics for classification? So if we would look at the mean absolute error, I think you can use it because in classification, your prediction let's say in a 0 or 1 case will be either a 0 or a 1, and your target value will also be a 0 or a 1. So you can definitely take the absolute difference of those. So what you will have is that, for example, if your target value is a 1 and you predict a 1, and this will be basically what this means if you apply it for classification is that this is the average sum of errors, because this is basically, this thing here is just the sum of the errors you made, which is actually not that interesting to look at in with this kind of formula. That's why for classification you typically look at something different, and I think with a couple of questions of yesterday it was already a little bit hinted at, but we are going to look at the confusion matrix. And yes, it is called the confusion matrix because it's actually pretty confusing if you learn about it the first time. And that typically has to do with the way things are labeled. So I will try to explain it very carefully. So again, what happens when we're doing classification problems is that we are actually uh, predicting a label. And most of the time we're just looking at a binary classification, meaning that we're either saying the outcome is of the positive label or the negative label. So in the case of for example, a spam classifier, you could think of, the spam classifier is going to say, yes, it is positive, meaning it is a spam email, or no, no, it's not a spam email, meaning the negative label. So in this case, we say the positive label means, although it's definitely not something positive to have a spam email, we say positive label means uh, it is classified as spam, and negative label is it is not classified as spam. And what we then have in this matrix is that we put the predicted labels on the columns. So this is really what the model thinks or predicted, and then on the rows we put the labels of the actual data. And then for each combination of actual label and predicted label, we are going to give let's say a certain category to that case. So suppose the model said it is negative, and the actual data also shows it's negative. We're talking about a true negative, meaning it is truly a negative label. And in this case, that would be that you classified correctly an email as non-spam because it was actually non-spam. However, if the model was not correct, you would have a false positive because the model falsely classified the email as positive, or in this case, falsely classified the email as spam. And that's why we say in that case, you made a falsely positive, you assigned a falsely positive label to this observation. That's why this is called a false positive. Similarly, you can flip this in the case that the actual label was positive and the predicted label was negative. In this case, false negative falsely classify non-spam. And again, if the actual label was positive and the predicted label is positive, you actually have a true positive because in this case, again, you correctly classified a spam email as spam. I hope that is clear. What I find confusing about this, and maybe you also encountered that during the COVID times when you got a result from your COVID test and it was saying your COVID test is positive. Does that mean, yes, I'm in the clear, but actually no, you're not in the clear because you actually had COVID. So I always find these kind of positive and negative labels to be pretty confusing. Um, but yeah, it's just something you need to get used to, because you will see these everywhere. Anytime you will read about classification problems, you will see these positive and negative labels coming up anywhere. Again, I also don't like the annotation you can have with that something is positive, because in one of the examples that we had beforehand is that if you have a classifier that would classify whether someone is a female or a male, then you need to assign either of those categories to positive and negative, which is also something I would not prefer to do, but that's just the way this works. So just be careful in these situations with interpreting this matrix. Now that we have covered the confusing notations, we can actually start looking at how can we use this when we're doing classification. Um, so suppose we have a data set of 100 emails, and for each of these emails, we are going to classify whether it's a spam or a non-spam email. So in this case, I just got rid of the positive and the negatives. I just put in the non-spam and spam on the columns to make it more easy for you. But again, in this case, we will say non-spam will become negative and spam will become positive as a label. And what you can do, based on each prediction you make, you can determine whether it's a true positive, whether it's a false positive, and that kind of stuff. So in this case, we will have uh, 57 true negatives. So we have 27 true positives, and then we have 6 false negatives, I think. And yeah, in this case, we have 10 false positive, because in this case, we made a wrong positive label because the positive label is spam. So we get this matrix for our specific problem. Then the first question is, of course, is okay, now, okay, that's nice that I have this matrix filled in, but I still don't know what to do with this. Using this matrix, we can start deriving important KPIs or metrics for our classification problem. One that's pretty obvious is something called accuracy, because what we could just do is consider the number of correct predictions we made, which is basically just the number of true negatives, 57, and the number of true positives, the 27 here, and sum those together and divided by the total number of observations we have. And this metric is called the accuracy, and it gives you insight in how many um, observations were correctly classified out of the total number of observations. So in this case, this means we classified 84% of the observations correctly. However, although this metric uh, seems very nice, it has a lot of pitfalls. And that is again something we have not covered in this course, um, but it's basically just the pitfall of averages, I think. Because suppose you have this model, which has an accuracy of 99%, so you think, yes, I made a very, very good spam classifier. But when you look at your confusion matrix, you start to wonder, this looks kind of weird. Because basically, what you can see is that your model started classifying everything as non-spam. Because every observation is in the end put in this negative column, meaning that this model actually doesn't have any predictive power, because uh, it's even worse than, now maybe not worse than a coin flip, but yes, maybe worse than a coin flip, because it just always will give you a negative label. And so that's really the issue with this accuracy metric. So it seems like you're doing very well, but you always have the pitfall that this model is just assigning always a negative or a positive label without actually looking at your inputs. So that's why we need to actually derive multiple of these metrics from the confusion matrix. Um, yes, so I don't think an actual discussion with 50 people is very useful here. So I will just try to give you a little bit of an idea of this example, because suppose you would be head of the IT department at your company, and you need to install a spam classifier for all your employees. You have the choice of two different spam classifiers, one on the left and one on the right. So you can see the data sets are the same, but the classifications are slightly different. As you can see, especially here, the left one identified 169 spam emails, while the one on the right only identified 67. So of course, the task for you is now, which one do I want to install at my company? So when you're the head of IT, you might think, okay, I don't trust my employees that much because I only have to have one weak one that is not that good in classifying an spam email as spam themselves. And I don't want to have the potential risk of having a data breach or a hack. So in this case, you want to have a spam classifier that's very strict. So in this case, you don't mind if certain emails go to the spam folder that should not be there, rather than having spam in your normal inbox folder of your employees. So in this case, we would rather have the spam classifier on the left, because this one filters out more of the spam. But suppose you would now flip the roles, and now you're one of the employees at this company. You would probably want to have the other one, because maybe you have these very important emails from your customer that will be sent to the spam folder without actually being spam. So in that case, you need to manually go to your spam folder and find that specific email that you're looking for. Again, having the risk that you actually might be clicking on one of the actual spams in that folder. So probably in the case of an employee, you find yourself capable of filtering out spam yourself. So you would want to have one that doesn't filter out important emails from your customers. So you can see different contexts might require different ways of looking at this kind of confusion matrix. And that is why, again, each context requires you to pick the correct features or correct metrics for your problem. So the metrics that we want to look at are, for accuracy, are, for example, so the recall on the left is 37. The recall on the right, what does that say? The recall looks at the percentage of spam that was identified. So this would be one of those metrics that the head of IT would want to look at, because he wants to be safe. So he wants to maximize, for example, the recall in addition to the accuracy. While again, on the other hand, when you're one of those employees, I want to have a spam classifier that's very precise. That's why we also have the precision KPI. This one determines the percentage of predicted spam that is actually correct. So that is something you can see here. One had a better one. The one on the right is more precise than the one on the left. So that's why it's very important to look at all these metrics simultaneously again. So you don't pick these kind of KPIs beforehand in your project. You always want to report on all of these KPIs, and then in the end, you can discuss with your client or your customer, which KPIs they find more important to look at. And again, this is really dependent on the context. So again, just to give you some formulas, and that's also why you actually need to learn a little bit about these notations for the different kind of parts in the confusion matrix, because when you look these formulas up on the web, you will find that you will see the abbreviations of each of these categories. So true positives are abbreviated with TP and so on. So the accuracy is just the true positives plus the true negative, which is the diagonal of this confusion matrix, and then divided by all of these, all four, so meaning all the observations. So this one is used to answer the business question, what percentage of emails is correctly classified? Secondly, you could also look at the error rate, which is very closely related to the accuracy, because it's just 1 minus the accuracy. But instead of looking at the diagonal, we look at the anti-diagonal. So we do the sum of mistakes. So this is false positives plus false negatives, and this will give you your error rate. Again, the business question is very similar, but in this case, we look at what percentage of emails is incorrectly classified. Next, so the precision. To calculate the precision, we need to do the number of true positives divided by the true positives plus false positives. So if you want to interpret these kind of formulas and find the business question yourself, I always imagine this confusion matrix and try to understand what kind of population of predictions I'm talking about. So true positives means the ones that are correctly classified. And then when the bit here below the division mark is here, true positives plus false positives. So when we look again at the confusion matrix, you will see that you're looking at the positive predicted column. So true positives plus false positive means everything that the model predicted to be positive. And then you can start to identify what this is actually answering, because now you check how many correctly positive classifications do I have out of all positive classifications I made. So the business question here is, what percentage of predicted spam is actually spam? Secondly, if we look at the recall, or also called sensitivity, again, if we want to interpret this formula, we check, okay, we have the true positives here. So again, the number of correctly classified positives divided by true positive and false negative. So meaning in this case, we're looking at the yes or the positive actual row. What does this row mean? This is basically everything that should have been classified as spam. So false negatives are actually observations that were positive but classified as negative by the model. So these two bits of our confusion matrix gives us everything that should have been classified as spam, and the bit true positive is only the bit that is actually classified as spam. So again, the business question here is, what percentage of spam is correctly identified by the algorithm? So out of everything that was spam, how many did we actually pick up on? Then we also have specificity. I'm not sure whether that's a mistake. Oh, this one looks at the true negatives divided by the true negatives plus the false positives. Again, when we can see these two make up the row of no, so of negative. So this is everything that is negative, and how many of the, again, in the case of what percentage of non-spam is correctly identified by the algorithm. So this is actually very closely related to the recall, I think. Yeah, but then just switching the positive and the negative classes. And this is one very important observation you should make, is because we have now always been talking about positive and negative labels. That actually, yeah, how to in this. The labeling, basically determine how which categories you pick as true positives and true negatives, or whatever, just as positive and negative. So, for example, in the case of a spam classifier, we now said positive is spam and negative is non-spam, but basically there's no given rule for that. So what you could also have done is just make the same matrix, but say positive is not spam and negative is, then everything would flip, because then a true negative becomes now the ones that are correctly classified as spam, and the true positives are now the ones that are correctly classified as non-spam. So be aware that the calculations are actually dependent on how you picked your ordering, and you can just swap them if you want, but then the interpretation of all these things will also swap based on the labeling you pick. It's an important observation for things we will see later in the presentation.
Sorry, David, we have a question.
Yeah, this is a good moment to just check some questions. Yeah.
Yeah, for now we have one that says, is recall the name of the metric in any setting, or is it related to the spam messages being recalled?
Okay. Are the defined namings for this metric. So it's either recall or sensitivity. I don't know which one will be used during the exercises, but these are like the actual definition of this KPI. So it's not related to the spam here. Yeah.
Okay, that's it for now, I believe.
Okay.
Thanks.
Okay. On to a couple more that we also have. I don't want to these because then we'll just keep on repeating the same kind of process. But there are two more that are important, which is basically the false positive rate and the true positive rate, because we were going to plot these on an XY plot in the end. So false positive rate is basically, again, we have false positives divided by n. N is in this case the total number of negatives. So in this case, we're actually looking at everything that should be classified as non-spam. Correctly. How many did I classify correctly as true positives? This is again one of those things we have already seen, but just with a different naming. So true positive rate is just the same thing as the recall we have seen in the previous slide. But for the next plot, we will see we typically talk about false positive and true positive rate.
David,
Yeah.
Sorry, I want to ask, are there some situations where you really cannot calculate the confusion matrix because you don't know for sure if it is false positive or false negative?
But then you have a data issue. So given that you have a data set with labels and you're sure about that, then you can always calculate it. So
if you don't have the labels already, I mean, you will depend on your algorithm, and you have some kind of, I mean, you have to find a way to trust the result even though you are not sure. Is that something that is possible in the machine learning, or you always have to have?
So you cannot train your algorithm without labels. So if you don't have labels, then you can't do machine learning. So, but I'm not sure what you're talking about, because it seems like you mix up two things. So there's always the first bit of the project where you have a data set with labels, and you're going to train a model on that data set. But then when you bring it to practice, then in real email and you do model is doing what it is supposed to do, you will always be able to calculate this confusion matrix. But you're right, in case of you're using this model in production and in real life, you don't know the labels, and then how to do that, that's a completely different topic, I think. But so you have to split those two different situations. I hope that is clear.
It's clear. Thank you so much.
Yes. Okay. Actually, before we're going to look at the plot that I was talking about, we will have to look at the decision boundary that we discussed yesterday and how it impacts your KPIs. Because suppose you have a logistic regression model or some other kind of classifier, these models typically give you a prediction probability rather than the label. So from prediction probability, you still need to go towards an actual classification. And like we discussed yesterday, that is something you need to do using a decision boundary. However, the choice of your decision boundary will determine how many mistakes you have. Because if you have a very strict boundary, you will inherently just predict positive clauses. So we don't see in this example the actual prediction probabilities, but just to give you an example what happens. suppose you would set your boundary at 0. That means that everything on the left side of 0 will be classified as negative. That's weird because prediction probabilities only go from 0 to 1. So if you check everything below 0, that means you will never assign a negative label. Everything on the right is basically just all observations. This is what you see here now in your confusion matrix. The decision boundary of 0 shows you that you will never classify something as non-spam and you will classify everything as spam. Now, what we will do, we will slide our boundary more towards 1. So, for example, we could set it at 0.5. Now you see, of course, everything on the left of 0.5 will be non-spam. In this case, apparently we had prediction probabilities between 0 and 0.5. So these are classified as non-spam, and everything above 0.5 is now classified as spam. Again, we can keep moving this decision boundary towards 1. And then we have a very similar situation as decision boundary of 0, because now it says everything on the right of 1 will be classified as spam. But again, prediction probabilities only go up to 1. So nothing will be classified as spam and everything will be classified as non-spam. And of course, I now show you only 3 possibilities, but you can basically set this value anywhere between 0 and 1, and this will show you a different result on your confusion matrix. That's why normally when you start your project, you just start with 0.5. But given your context, you want to see if you can optimize your decision boundary for your context. So for spam, that's not that interesting. It's not a very interesting example. But again, if you're in a more medical context where you need to be very sure about handing out medicines or classifying if someone is actually ill, you want to adjust this boundary given, such as it suits your context. So be aware that this is actually, you could say something is a hyperparameter. I know we have not covered that really, but this is something additionally you can choose on top of the actual model. And that will definitely have impact on how good your model is in the real life. Boundaries and then looking at the confusion matrices, we typically look at something called an ROC curve, which stands for recoil operator curve. In this curve, we are going to calculate the true positive and the false positive rate at different decision boundaries. We will basically calculate for every decision boundary between 0 and 1, and then see what kind of impact it has on my true and false positive rates. So one of these points on this blue line that you see here is corresponds to one decision boundary, and that specific decision boundary has a specific value for the true positive rate and the false positive rate. So 2 important things you always will observe with these ROC curves is that they will go through 0, 0, and they will always go through 100, 100. And that has to do with the thing we saw here, because basically the decision boundary and the point here in the upper right corner corresponds to the decision everything is classified as positive out of positive, but then also here the false positive rate, it means you basically classified everything that was negative positive, meaning that you also end up here as 100%. And on the contrary, the 0, 0 point here on the graph corresponds to a decision boundary of 1, because in this case everything is classified as non-spam, and that's also what we saw on the previous confusion matrices. So all the points in between are values that are in between 0 and 1 for the decision boundary. The nice thing about this one is that you get a feeling of how good your classifier is doing, because you can actually also see the perfect classifier in this graph. And the perfect classifier is basically the classifier that if you give it a slightly room to classify something as positive, it directly finds everything that should have been positive. Basically saying that all your positive predictions are somewhat, so we'll give you some kind of prediction probability of 0.99999, very close to 1, and maybe even 1. And then when you become more and more and loose, you will start to make more mistakes. So that means that your false positive rate will also go up. And then in the end, this perfect classifier also ends up in this 100% point. And then, yeah, I will discuss this when, yeah, basically these lines will never go below this classifier with no predictive value, because you can basically interpret this line as a classifier that's just doing a coin flip every time. So that is basically saying, when I make a classification, I'm 50% sure it is correct or incorrect. So that's why this one shows you this nice 45-degree line. The nice thing about this plot is that you will never plot one model in it, but you will probably fit all your models you have fit inside this plot. And then you can actually start to compare different classifiers with each other, which is a very nice feature of this. We, in addition to making the plot, we also calculate a new KPI we have not discussed yet, but it's called the curve, or typically abbreviated by AUC. The AUC is just giving you the value of the area below your ROC curve for a specific model. So you can see the perfect classifier would be 1, because if you calculate the area below the one I showed you here, so it's basically the whole rectangle, which is 1 times 1 is 1. Oh. And then the coin flip model, so the one with no predictive power, is exactly 50% of that, meaning 0.5. So the AUC will always be somewhere between 0.5 and 1. And the closer you are to 1 means the closer you are to the perfect model. So you want to optimize or maximize this area under the curve. Typically, I would ask this question to you. So maybe I will give you, so you don't have to answer it. It's also fine if you want to, but I will give you like 30 seconds to think about this question, and then I will just give the answer. Because I think this is interesting. If all lines of the line, just think about it for a couple of seconds, and then I will give you the answer.
If it is down of the line, it means it doesn't work. Basically, it's not doing anything.
No, that's not. But I understand why you would say that, because then you actually say, okay, you have a model that's worse than a coin flip. So I agree with your opinion. You would say it's very bad. But the nice thing here is, or the nice thing, it's just one of those features of the confusion matrix, because what we can do is just reassign the labels to our model, saying, previously I classified this as positive, but I'll swap it to the negative label, and the negative label will be swapped to the positive label. Basically, what will happen to the line is it will be mirrored across this 45-degree line, and then again it's above this line. So every time you will see a line that's below the 45-degree line, you should actually just flip your positive and negative labels, and then your graph will be nicely above this 45-degree line. So it's just a very just a trick, but it's good to be aware of, again, that the positive and negative label assignment can give you something that doesn't look like this. So if at some point during your project you would have that all your lines will go below this 45-degree, then just remember you can make it happen that everything is above the line by just reassigning your labels. So sorry. So what did we learn? So for regression, we have learned that we can look at more KPIs than just the R2 and adjusted R2, because we have now also covered mean absolute error, mean percentage error, mean squared error. So we have a couple more. And you should always report on all of these metrics. For classification problems, we have discussed that these KPIs are not that good. You should rather look at the KPIs related to the confusion matrix. And indeed, they can be confusing based on this positive and negative labels, which are not so intuitive. Very important is that mostly by default, Python packages will try to optimize accuracy. Be aware that accuracy is not always that good, because it doesn't capture the cases where it's just doing always a negative or always a positive classification. And in those cases, you want to look at more of these KPIs, and I would always also report on the precision and the recall. And these can also, the true positive and the false positive rates can also be plotted on this ROC curve, which gives you some comparison between models. So before moving towards the next bit of theory about model performance, I want to see if we have one or two more questions.
Yeah, so we have one question that, we always say that if the decision boundary is closer to 0, then we have more false positives.
Maybe practically yes, but in theory I don't know. So suppose your model is always predicting with 0.00001, so it's just always doing that prediction probability, then you need to bring it pretty close to 0. So not necessarily, but in practice, I would say the closer you are to 0, the more positive predictions you will make, meaning that you can make mistakes. I think in general your argumentation works, but in theory there might be some exceptions.
Okay. Then we have, I think, 2 answers of the question that you asked before. I think we covered that. And we also have another question that says, what does a decision boundary of 0.5 mean for false positives and false negatives? Is it a minimization of false predictions?
No, 0.5 basically means you need to be at least 50% sure to predict something as positive. I think that's the way you can look at it. It doesn't say anything about minimization of false predictions, because that's actually the bit where you need to pick it yourself. Hope that answers this question.
Yeah, I think that's it for now. Thank you.
Okay. Let's move on towards the next bit of theory. So we now have discussed a lot of ways to identify the performance of a model, but we have not really talked about how do we make sure that we can get some feeling of the performance in real life, because like we have already discussed a little bit yesterday, you can just you have this training data and you can just train your model on the training data, but then it basically ends there. How do I now understand how good my model is in practice? So there are a couple of different methods, but the most simple one is just splitting your data in training and test data. And the idea is that you only train your model on the training data. So it will give you all these KPIs we have discussed for your training data. And then you also have your test data. Again, you can then test your trained model on this test data, because it has not seen the data. It gives you some kind of insight in what happens when a new observation I have never seen arrives at my model. Is it still doing a good prediction? So these KPIs we've been discussing, you will always calculate them for the training data and the test data, and then start comparing the difference between them. Yeah, so indeed, the training data is used as to train your model. Test data is just to give you predictions, and then the performance of your test data is an estimate of the quality of the model in real life. So this will help you identifying the cases of high bias, high variance, or underfitting and overfitting. Because in the case of underfitting, you made your model too simple, which means you're in general will make a lot of mistakes because you just, yeah, don't capture all the relationships that are in the data. So what happens is that your KPIs will be bad. But in the case, it is a quite robust model because maybe it just fits on the most important and it can at least determine something. In that case, you will see that your error, so that's the one in blue, is the one that's obtained by finding the error on the training set, and then the validation error, that's the same, meaning you have kind of a robust model because training and test is very similar behavior, but you don't have a very good model. The other way around, if you have a very low training error, you might think, oh yes, I made a good model, but then when you test it on the test set, you will see that your test KPIs are very bad. So for example, when we're talking about R2 for linear regression, maybe your training R2 is 1, but your test R2 is 0.5. That means that the, yeah, performance on the test and the training set are way, yeah, too different, meaning that you're probably doing something of overfitting on noise. So that's the way you can look, why this approach can help you determining your under and overfitting issues.
Sorry, you mean the R2 is the same as R square, or I'm confused?
Yeah, sorry. That's yeah,
Okay.
R2 is same as R square. I should call it R square. Thanks for this. So that I was talking about, just if anyone else was confused, I was saying, if you are calculating the R square metric for linear regression on your training set, you might uh, see an R squared of 1. And when you calculate it on your test set, you will see something as 0.5, meaning that there's a big difference between those KPIs. And then you're in this high variance case where training seems to be fine, but you overfit on noise, and therefore you can't actually generalize the things you have learned in real life.
It's normal to be confused. We just finished the confusion matrix.
Exactly. um, yeah. So the quality of fit in general, if you just do it on the test training set, doesn't give you any idea of how your model is doing uh, when it's actually doing some forecast in real life. And that's why we need to do something else. So we now have just discussed that you can split it in train and test, but actually we will see that this is probably not the best approach. um, there are multiple approaches to do something similar. So the method we discussed in the last slides is actually called validation set approach, meaning that validation set is actually your test set. So you set aside some observation you will never use for training, and then you test the performance on this. But there are actually two more methods to do this, called leave out one cross validation and k-fold cross validation. And so let's discuss why we need them and what they do. So again, just to show you, to reiterate what is validation set approach, you have one large data set um, of n observations, and you're going to split it maybe into halves. You can also split it different, but in this example, we split it in two halves, and then the part on the left is used for training and the part on the right is used for testing. It's a very easy approach because I saw you last time in the what you saw last time in the linear regression exercises. This is just basically one line of Python code, so it's very easy to use in your project. But the downside here is that it really depends on how you make the split. Because yeah, maybe exactly in the half, but you also random of your observations and then do a 50-50 split. So there are a lot of different splits you can make, and the different splits will actually determine how good your trained model is. Meaning that the performance indicators you will obtain will be very different. So I have to check this one. So this one is basically the complexity of your model and then the error. So in this case, you can see, yeah, it's the best one to look at the right. You can see each of these lines is a different split of your training and test set, and then it calculates the error of your. I think this should have been the test score. You see that the variation between, or the performance between different splits is very different, because this one is actually pretty high and this one seems to be very low. So it just depends on what split you made to see how good your model is doing. And also you can see the trajectory of making your model more complex for those different splits. You can also just validate this for yourself. So suppose you have a couple of data points that are very unique but show very good relation, and are typical examples of the relationship you should model. If you don't include them during training, the model cannot pick up on those nice relationships you have in those observations. So it will actually miss the relationship to model, and then it needs to test on it, and it will probably uh, not work very well for those observations. So that's basically why you will see this kind of a variation between different splits. That's why we actually want to do have a different method that doesn't have this downside. So there's actually one more downside, and the downside here is that it actually overestimates also the real error rate, and that's because you set aside maybe 30 or 50% of your data. So the model is actually not able to use that data to train. But in real life, when you're actually going to use your model, you will always train your model on the full data set, because in that case, you're not that interested anymore on how good it is performing on this test and training set. You just want to have the best model that's trained on all the data. So in this case, you set aside a pretty large chunk of your data that cannot be trained, meaning that probably your model will do better in real life a little bit. So that's why it's actually also overestimating your real error rate. Um, So how can we deal with this issue? So what we can do is just make sure we don't set aside a very large chunk of data for training and test. So what we will do with leave out one cross validation, we will do multiple model training. So we will do multiple splits, and in each split we will just leave out one data point. So in this case, in the first row, we only leave out observation 1, and the rest we keep for training. In the second row, we leave out only 2 and use the rest for training, and so on and so on. Each of these rows corresponds to one trained model. So what we will do, we will do the first split, train our model, calculate the metrics. And then we will go to the next row. Again, we train our model on a new split and also calculate the scores or the KPIs for both the training and test. And we will do it basically for all the rows. So we will retrain the model n times and also recalculate training and test scores n times. Meaning you end up with, in the case of linear regression, you would end up with n r squared for the training sets and also n r squares for the test set. The next step would be, because that would be if you have maybe 1 million data points, you have a lot of these R squares. So instead of just looking at them separately, we rather look at the average of those scores. So in this case, we use the mean squared error rather than the R squared, but I think in both cases it would work. So in this case, we calculate the mean squared error for each split and then average over it. And in this case, it's probably most interesting to look at the test error rather than the training error, because this one is interesting for the for the performance of our model. The downside, of course, is that if you have a very complex model that you need to train, training something 1 million times can take a long time. Already doing 1 million times a training of 1 second is already 1 million seconds. I'm not that fast with calculations, but I guess that's a lot of hours. So you don't want to do that because maybe you want to do a slight modification of your model and then you need to do everything again. And that's why we typically don't do these small batches of one, but we do larger batches. So in this case, we also don't really care about how large the batch is that we set aside, but we are more interested in how many of these retrainings we are doing. So in this case, that's something called k-fold cross-validation. We're more interested in how many of these replications of model training we are doing. So in the case of K is 5, we will do 5 model trainings, meaning that we will set aside 20% of our data for testing and 80% for training. So in this case, we use the first 20% for testing and then the other 80% for training. And then we make sure every data point is at least once included in one of those batches. So you see, in the next step, we pick the other 20% of our data. In the next step, we move to a separate and so on and so on. And then in the case of K is 5, we only have 5 of these rows here. And then that means we are going to retrain our model 5 times on the different train test splits, recalculate 5 times our test scores, and then again calculate the averages. But then in this case, not over all data points, not 10 in the case of leave out one cross validation, but K, in the case of K, the one we picked. So 5 or 10 is something you typically use. So this will be an average of 5 or K different KPIs. So the nice one here is that when you look at the variations between, so when you look, at the variations you have, because in the case of leave out cross validation, there's basically one option, because what you do, you always leave out one and keep the rest. So there's not variations between how you choose the splits. So you can see you typically have one line that looks like this. In the case, of course, when we are talking about k-fold cross validation, we can of course have different kind of splits here. So again, this method is kind of dependent again on how you choose these splits and which data points you include and exclude. Although you cover all data points, it still depends on how you pick these at each step. But the benefit here is that if you again average them, you're pretty close to your leave out one cross validation. So you're doing very good actually. So you see again, each line on the right plot shows you a different way you do the splits for 10-fold cross validation, but you see it's way more robust to slight variations in the way you pick your training and test sets in each of these steps. Just to compare them all, so this validation set approach is very simple, but it comes at the cost that you have high variability. Actually, the funny thing here is that I would always recommend to use it in a project, because maybe you're at the start of the project and you have your data set and you're very enthusiastic and you just want to get some results at the end of the day. Then you don't want to start implementing something very complicated. What you can just do for yourself is I just start with doing a simple test trains set and then set up the rest of my notebook, just test a little bit. Kind of machine. Nice. Little bit. This is just you will the benefit of the leave out one cross validate always give you the same result. Doesn't really matter on any kind of how you picked your test sets. So it's very nice. The downside here, what I already mentioned, it has very high computation time because you need to do it for every data point. So it's very costly, and that's why you actually have that this k-fold cross validation is the best of both, because it has smaller computation time than the leave out one cross validation. It has very small bias, although you still need to have different kind of possibilities to pick your test sets, but it doesn't show the high variation, the validation set approach, and that's actually why when you will look up someone else's machine learning projects, they will typically use k-fold cross-validation. Then, of course, we use 5 or 10 in most cases. Again, this relates to what kind of model you are using. So if you have a model that takes a long time to train, you might want to use 5 because then you basically reduce the execution time of the algorithm by 50%. But of course, when you pick k is 1, you're basically that's something, or k is 2, that's something you don't want, because then you're becoming closer and closer to a validation set approach. Because in the case of 2 splits, that's very similar to what we had with validation set approach of just k is 1. Even don't know if that works, but you can also just have 1 split and then it's basically exactly the same. So you want to prefer picking k as 10 whenever possible, because that's probably better, because you have you're less reliant on the way you pick your test sets. But in certain cases, k is 5 will work also. So yeah, in the end, you might start with validation set approach, but I highly recommend to always use k-fold cross validation when you start really assessing how good your model is doing. So validation set approach really only at the start of your project. Yeah, so again, let's take a little bit of time to see if there are any questions. So I see indeed someone said VSA is what we used yesterday. Correct. And in that case, we used VSA with a split of 30%. Yeah. I think we don't have any other questions. So validation is prediction. Yeah. So validation does not mean prediction, but validation means test set. So validation set is the same as a test set. Okay. So I see I've already been talking for an hour, and I want to move basically directly to the next bit of theory. So that's why I would recommend to just take a 10-minute break, and then we move towards decision trees. This was really the hardest bit of theory for today. So the next bit will be easier. And I think in total, we will only cover uh, three quarters of minutes of theory. So basically today we will also have, let's say, 2 hours for actual exercises. So let's take a 10-minute break. Or 9-minute break now. So let's be back at 15. And then we will continue with the decision tree part. See you in 10 minutes. All right, I hope everyone is again back and had a good refreshing moment in order to again be able to digest all the new information I'm going to send to you. So in this next bit, start models you could almost talk about, and they're very nice to use in practice. Maybe not in this format, but we'll see later on in the last bit of theory how you can actually build very powerful models using decision trees. So decision trees can actually be used for regression and classification. Um, called after a normal tree because they are very similar to, they look like an actual tree, especially when you would put the tree upside down, of course, because the branches here are going down typically. So a decision tree, um, yeah, at the start of the decision tree here, so in this case we have data about per people that whether they are a smoker, yes or no, their age, their diet, and whether they have more risk of less risk of having lung cancer. So in this case, we want to predict or classify a patient as having more or less risk of having lung cancer. So what we do in the case of a decision tree, we start using the data we have available. So we have information on the patient whether he is a smoker, yes or no. So what we do in the case of yes, we will move to the left bit, the left subtree. In the case of no, we will move to the right subtree. Then in these subtrees, we can ask a new question to our observations. So in the case of a left subtree, we are going to ask the age of the person. So in the case the person is younger than 30, we will assign less risk of lung cancer to that person. If again he's the person is older than 30, he will be assigned the label more risk. So also good to mention here, the labels, the classification labels are in this case less risk or more risk. So in the case more risk would be maybe positive label, less risk would be the negative. To ask different case of whether someone is having a high risk of having lung cancer, the first thing you probably ask yourself is, does he or she smoke? And then, of course, the next one would be, okay, if a smoker, then the longer you are smoking, and that correlates, of course, that the older you are, the more risk you have. So these decisions you at each of these and so-called nodes, this is what we call nodes, are very intuitive. And in the end, the other thing I think that's called a leaf are the ones that let's say the nodes at the end of each of these subtrees. Of course, this is just an example. The question still is, how do we actually mathematically derive our decision tree? I'll definitely later on. Actually show you how you can derive decision trees using a very nice visual example. So in this example, we will cover a classification problem where we have house information available and we need to predict whether the house is located in San Francisco. When the house is located in San Francisco, we color them with green, or whether the house is located in New York. Again, when the house is located in New York, we assign the blue column. The year it was built, the number of whether I think the number of bathrooms, the number of bedrooms, the price, the square feet, and eventually also the price per square feet. So we have these bits of information available, so we can do all these. We can make these decisions we did previously also based on these of information. So, of course, first step is do we want to start because we need to make one decision at the start of a decision tree, which of these features do we want to use for the first split. So for example, what we could do, if you know a little bit about the the geographic of America, you might know that San Francisco is very specific hill, or maybe there is this could also be one of the skyscrapers that's very high. I don't know how actually this thing is measured, but you can see it's a pretty good indicator, first indicator we can use to classify something as San Francisco or New York City. So what we could say, what we could say is that if we just would do a very simple decision tree where we just make one decision, what we could say is, okay, my decision is when the elevation is larger than 250 feet, then I assign label San Francisco, or below 240 New York City. If we can find different splits, or we can make better classifications based on that. So in that case, what we also know about New York City is that it's a very, very expensive area to live in. So what we could do is make a 2D scatter plot of the price per square feet on the x-axis and the elevation on the y-axis. So what we see, what we are seeing here, is that the data really gets stretched out. So we can see that this there starts to form a very nice green cloud of data points here, and a very nice blue cloud of data points here. Set a decision. Subset of data points that only belong to New York. So this already gives us a lot more information in how we could set up this tree, because for example, now we already discussed the one about elevation. We will keep at 250 feet and 740, the 250 feet decision mark. And now for the price per square feet, we can see somewhere 70 right is New York City. So we could do first a split on elevation, so based on our 240 feet. Next split would be based on price per square feet, where everything above 170, 76 is classified as New York. And then, of course, what we could also do is, again, introduce a new feature, but that would be very difficult to actually plot in these kind of so just we now classify these houses is actually, although it's a little bit fake, you can see this blue rectangle. This blue rectangle is exactly all data points that are between 1,776 price per square feet and 4,600. So that's the x-axis here. So the rectangle goes from there to there. And the width of the rectangle is defined by 0 to 250 feet. And every data point that falls within this rectangle will be classified as a house in New York. So in this case, you can see we would make, in this specific rectangle, we would make 0 mistakes. Except if you would now, for example, assign that all the points are San Francisco, of course, we still make a lot of mistakes. So we need to refine and refine. But before we do that, we want to actually discuss, of course, we now set this elevation split at 242. What does that actually mean for the number of true positives and false positives that we generate? Or the mistakes that we make. Maybe that's easier to talk about. So what we see if we would do this split here, so you can see this is like a histogram of the elevation and then the count of each label. In the case, the labels in this case, the city the house is located in. So you can see if you would pick the split to 42, everything on the right is San Francisco. So in the right subtree, we would basically end up with 47 San Francisco data points and 0 New York data points. So that's nice. In this case, we have only these, so we could basically just say we stop our decision tree here because we're done. This is fine. The left side, if you look at the left subtree, you see there is a mixture. So it's almost 50-50. So this, of course, ends up in quite some mistakes. So if we would say this would all be in New York, then in that case we would only have an accuracy or correctness of 63%. But of course, you can also pick a different split point, decision point. You can basically pick whatever you want. And of course, like we saw with the decision boundary for confusion matrices, the decision boundary has impact on the number of mistakes you will make. So in this case, if we would pick just 0 feet, then yeah, and I'm not sure how we are going to predict here, but in this case, I think we predict the right-hand side as San Francisco because there are more San Francisco houses, which means that all the New York houses will be incorrectly classified. That leaves us with now, with this split, only a 56% correctness. So the correctness at each decision really depends on how you set your decision point, like with the decision boundary. So I will not dive now in how you could split this, but the best split is probably this one. That's one. First split on this, but then again, we can start doing a new split. And we have already really said that if a price per square feet could be also a very nice one to do a split on. So in this case, we are going to refine our model and our performance by introducing a new split on price per square feet. And then again, we end up with 2 new subtrees. And on the right-hand side, we're not going to do price per square feet. Rather, we're interested in price. Again, we do a split. And you already see this one is very closely to 100% having San Francisco. So that's nice. By the way, the size here of the circles corresponds to the number of data points that fall in the circle. So the smaller the circle, the less data points are reaching actually that leaf. And of course, what we can do is just continue this process until we are happy. So we can do way more splits. Actually, what we could potentially do is introduce as many splits as we want, and then you would basically end up with 100% correct, or let's say that each leaf here, so really the leaf is the last node in each in the algorithm, only consist of data points of one house. And in that sense, you will reach your 100% training accuracy. And of course, that is something we have already discussed. There's the bit of underfitting and overfitting where you need to be careful. So, for example, in the case of growing your tree until you have reached nodes with only houses of San Francisco or New York, you might end up with 100% correct training score, but you will see that your test score is less, which actually means that we're overfitting on our data and making. So what you can do with these decision trees is really, especially if you have continuous data, just make the decisions that each data point falls exactly within the one of those boxes, such that you end up with pure nodes. But that's not what you want because that's overfitting. So probably in this case, we want to look for less complex models, so less complex trees. And less complex trees basically means making less decisions. So you can see instead of making somewhat like 50, we can just make 1, 2, 3, 4, 5, 6. And then we end up with a more robust and probably less overfitted model. But again, our training scores might go down, but at some point they will be very similar to our test scores, and that is actually the situation we want. So I hope that this example showed you that decision trees are very intuitive and that there are ways to prevent you from overfitting by making sure your tree doesn't become too large. But we still have not really talked about, for example, the mechanism how to choose your optimal split. So that's something we still need to discuss, and how you can make sure your trees don't grow indefinitely, let's say. So that will be the last bit of this bit of theory.
Sorry, David. We have one question. Can you hear me?
Yeah, I can hear you.
Okay. Can one observation only be at the end of one branch? In the initial lung cancer example, it looked like an observation could end up at the end of multiple branches.
No, so I'm not sure why the example. How? Yeah, so the idea is that each observation can only end up in one of those leaves. So an observation should not end up in multiple. So I don't know. I'm not sure if I can look at the example again. Because, for example, smoker here is just yes and no. So there's nothing in between. So the observation will go either left or right. So there's no. Yeah, here it's a little bit. Maybe this is the bit where it was fake. Less than 30 and larger than 30. Maybe we should have said smaller than 30 and larger or equal to 30. So in that case, you just have one age, so you either end up left or right. So especially in the left tree, we are already proven that one observation can only end up in one. And then on the right hand side, there's one question about diet. And in this case, the diet is just having only labels good and poor. So also here, one observation can only travel to either the less risk or the more risk. So no, in this case, also each observation will go to one leaf node. And that will also, that will basically always be the case for decision trees. They should not end up in multiple leaf nodes.
Okay, thank you. That's it for now.
Okay. So about choosing the best split. The best split will probably mean that you want nodes as pure as possible, and pure nodes basically means that the purer the node, you will have only one version of the node. Sorry, I need to rephrase that. Pure nodes are basically nodes with only one label in it. So in the case of classifying San Francisco or New York, we end up with a pure node if we only have a leaf node with only San Francisco or only New York. So only C is a pure node. A and B are not pure nodes, but at least it looks like that B is purer than A, because as you can see, B has three, in this case maybe New York homes, and the rest is all San Francisco. So this will be like 70% will be maybe San Francisco, and the 30% here, New York. So it's not close to the 100% purity we have here, but this one will be 50-50. So this one is definitely not close to pure, but B is closer to pure. In the end, we of course want to have C, because that's better. But of course, you don't want to end up in the case of overfitting, but that's a whole different question. That's not really related to what a perfect split is. So a perfect split is that you want to target as pure nodes as possible. There are actually formulas to calculate pureness of nodes. So I don't want to cover how these formulas are derived, but just to show you, in the case of a binary classification problem, so we look at the proportion of a certain class in the node. So basically meaning that if you're at 50% here, then you don't have a very good node, because that means 50-50. And in that case, the purity measure is at its maximum, so 1. So 1 means, in this case, not pure. What you want in the purity measures is that they go to 0, because in 0, you're either in the case of having one class 0% represented or one class 100% represented. And exactly those two are pure nodes. And then in between, the purity measure grows towards 0 and then decreases again to, the purity measure increases to 1 and then decreases to 0. And yeah, the different purity measures you have available have slightly different graphs, but again, all the graphs show similar properties. I think typically the Gini index is used because it's not as computationally heavy to calculate, because this logarithm is an expensive operation. So that's why you will, by default, I think, use this Gini index rather than the entropy. And then what you can do, so now the question is, how can you use it in your decision tree? So what you can do is you can calculate the purity of the node you're going to make the split at. Then you make a certain split, and then you calculate the purity of both nodes that are a result of the split, and you take the average of the purity of those two nodes. And then you want to make the nodes in the next step as pure as possible. So you're just not focusing on maximizing the purity of just one node, but you're maximizing the purity of both nodes that are a result of the split. And that's basically the increase in the purity before and after the splits is called information gain. Again, I don't want to go in details here, but just know that there's a small mathematical principle to decide on the best split available at each step. And that is done based on the purity of each node. So again, what did we learn? So we learned that we like pure nodes, and we learned that we can use different measures of purity to decide how we can actually do the split. And in the end, we use information gain to decide on the best split. So before I go to the next bit of theory, let's see if there's questions.
Yeah, the one asks, do the branches need to be just 2 or can be more? And I believe the other one is similar, or can we use decision tree only for 2 categories? I'm not sure.
Let me think. I think you can use decision trees for multiple categories. I think that's perfectly fine. Use it for more. Also in the exercises, I think we make it easy. We just use 2, but it should also be possible to have multiple. But then you just have multiple categories that you need to take into account. So I see overfitting questions. We will definitely cover that in the next bit. I hope. I hope I didn't remove it from the slides, but should be in there. So the implementation, I wonder how the implementation is. It's basically just what I said. You basically calculate the information gain. So you calculate how you increase the purity of nodes based on a split, but then you calculate it for various splits and then decide the best split. So that's basically how it works. But then again, of course, how it's implemented in Python, you can look at the source code if you really want, but that might be very difficult to look at. So about overfitting, let's dive into that. Overfitting is done by making the tree smaller, and there are so-called hyperparameters you can set on your decision tree model. That of a tree is basically saying how deep can my tree grow. So how many decisions can I make until I need to stop? Then the maximum number of leaves is basically the number of leaves you have at the end of your tree. So you can say I just don't want more than 10, for example. Another one is the minimum number of observations that should be in each leaf node. So of course, when you would say 1, then you basically allow your tree to grow until each leaf node only contains 1 observation, and that is definitely overfitting in most cases. So in that case, you could say, I want to make sure 10 data points end up in each leaf. So in that case, when it has 10 data points, it will check, can I do another split? But then in that case, you have 10 and it's not allowed to do a split. So then the algorithm stops. And also more technical one is information gain. I would not recommend to play with that one. I think those 3 play with. And of course, values. You calculate your training, your test scores with cross validation. And then again, you redo this, but then again, you pick different parameter values. And again, you calculate your test scores and so on and so on. And then you pick the best model basically. So that's basically, you see it with this cycle. You do cross validation, you estimate the performance, you change your parameters. Again, you start doing the cross validation, estimate the performance. And at some point you need to you say, I'm happy enough with the current model. So what you can do is, for example, with number of leaves, you can start with maybe sorry. So you could say I start with 100 leaves that I allow, and then decrease the number of leaves, and that might reduce the number of errors you make. And these kind of plots, they look very similar to those elbow plots we have we've talked about earlier, basically saying whenever you see flattening of the improvements, you don't want to increase it anymore. Is one way choosing the best set of hyperparameters on your decision tree. Let's see if there's a question about this. That's the order of nodes attributes.
Yeah, does the order of the nodes attributes in the tree structure influence the results accuracy?
Yes, so yes, that really matters. Because maybe, and that's actually also something the algorithm takes into account. It will not only say, you don't supply the decision it need to make. It will actually consider multiple features and then calculate multiple splits for each feature, and then decide for each of all of the things it calculated which one is the best. So it'll also decide for you which split should be done at the start, and it has impact on your decision tree performance. But again, it's taken care of by the model itself. Okay. So I think I also answered the second question. So the decision is made by the algorithm and not so much by ourselves. All right. So we now only talked about how you can do classification with trees. So in that case, with the classification with classification trees, we have that observations reach nodes, and then in the end we check how many percent of each category or each label ends up in the node, and then say we pick the one that is most represented. So if we have 80% New York in the leaf node and 20% San Francisco, we will say when a node ends up in this leaf, I will classify it as I said New York, I think, because that one had 80%. So that is how classification trees work. We have discussed them. Similarly, you could also do it for regression trees, but I think regression trees are less intuitive because what happens with regression trees, you basically make the same. So you want to make predictions, so that's different. So what you want to do with regression trees is that you still make those splits, but in the end, rather than having labels ending up in the leaf node, you just have a average value of the target. So you will have maybe 10 different observations, all with a different target value. And then what you do, you take the average of all those target values, and that will be the prediction when a node ends up in that leaf node. So that's how you can do regression trees. You can even make it more complex. So what you can do instead of just taking the average, what you can do is train a model for example, the linear regression model on that. So meaning that if you end up in a specific node, you will use a specific linear regression model to do a prediction. So to make it a little bit more visual, hopefully this makes it more intuitive what happens here. So in the case of a regression tree, you can see what happens when you set different kind of maximum depth. So maximum depth set how deep can my tree grow. So in the case of a maximum depth of 5, where you can actually see this model is starting to overfit, because apparently this data point you see here between 1 and 2 ended up in a specific leaf node, and then the model is going to predict exactly that value. So that's something you don't want, where actually when you look at different parts of the predictions here, it really predicts the average of all those data points that you see there, and then it predicts it with a flat line. So yeah, I have actually not used these kind of regression trees that much, or regression decision tree that much in practice. Or maybe in that case, the model tree is a little bit better, because then you can see, okay, I make a split here on my data, and on the left I train a new model, and on the right I train another model, and then again I just keep on splitting, and then I basically make very small bits of linear lines and paste them together. So that might be a little bit more performant, but again, I think these become less intuitive to interpret, while actually the classification trees, I think you can basically very easily explain what is happening to someone, where this one is a lot more complex. So in general, they are very intuitive, but what I already said, if you have intuitive and interpretable models, they are typically less accurate, and that's also what we see with decision trees. In the last bit of theory, we can see how we can combine decision trees into very accurate models, but that's something I want to postpone a little bit, because I think now is a good time to start doing exercises and start doing the project. Just check if there's one more question. I don't see them. No.
No, I don't
So
think so.
now is a nice time. I think we can take 1 hour to work on this exercise. So that means we go until 10 to 5 my time. And then we have, I think, 20 minutes of theory, maybe only 15. Then the rest of the time, again, we work on the project. In this case, we will only do one set of data. So let me just show you what you should start using. So for this exercises we're going to do, we should use the so-called I'm sharing the right screen. The water quality classifier with certain features, and based on the features, you should try to predict whether the water is potable, yes or no. So again, I made a start. Oh, this is actually the answer sheet. Let me just upload the notebook for the handout. So the water potability classifier piece of code to read the data and do some small transformations, I think. Let me check. So this is just exploring your data. Then again, we want to, right, here's some data about filling in missing values. In this case, we do it very easy. We just say, we check the mean of non-potable water, and we check the mean of potable water, and then fill those means in for those specific observations. For the value and another value. So we just fill in the means to make sure we don't need to throw away data. So again, you can look at it, but I already gave you the pieces of code to make sure that it works. And then the idea is that you have the features are equal to everything except the potability, because that will be the target of our model. And the idea here is that you start doing decision trees and cross-validation. And then, yeah, that's basically the thing I would recommend to start with. One nice thing that you can play with is, let me just show you that, because that's very powerful. Is actually you can make plots of your decision tree. So the water potability CSV. So let me just execute all these cells quickly. Also, I already imported a lot of different functions for you, just as hints for later on, that you don't need to look for all the correct models in scikit-learn yourself. So let me just execute the cells I just discussed. And then I have included a small bit of code that can help you make a plot of your decision tree. So if I would now make a plot of my decision tree, and I didn't specify anything, so I think this decision tree is really growing towards an overfit tree. You can see I specified the maximum depth to visualize as 4, so you will only see a depth of 4. But you already see this is that this one probably will tend to overfit. And then what you can do, just as a nice exercise, is see what happens, for example, if I say max depth is 3. What happens to my decision tree? And then you will see, yeah, okay, now this is exactly my decision tree, so you can see it fully. But then you can also say, maybe I want to play around with, I'm not so sure. Can I think about another one? So minimum samples at the leaf, for example. Yeah, maybe we can, minimum samples to split. I see samples are, I don't actually know how many data we have. Around 3,000. So maybe I say I want to have 300 data points for each split. Then probably okay, now it looks very similar. So maybe I say I need 1,000 data points for splitting. You can see again, based on this feature, your tree will be different, because you basically give it different ways to grow. So just play around with that and get some feeling on what all these different hyperparameters mean. Hyperparameters are basically very easy to identify, because you can see them in the documentation. So in this case, hyperparameters you could play around with are the criterion, which is now called Gini, but you can also do entropy, for example. You could change the maximum depth, the min sample split, min samples leave, and max leaf nodes. I think those 4 probably the most easy one to understand. And then again, if you want to know what they should be doing, again, check out the decision tree classifier documentation of scikit-learn to get some feeling about that. Okay, so I think we should again go into breakout rooms, and let's take until 5 to 5, right? Yeah, 5 to 5. Let's take a whole hour to work on it, because I think especially the k-fold cross validation will be difficult for the first time to implement.
Okay.
Yes. Yeah, can you share in the chat the notebook and the dataset?
Right. Hopefully I can easily get them.
I will create around 6 breakout rooms, so it's gonna be 9 to 10 participants.
Yeah, and in this
Um,
case, I would highly recommend to maybe that I don't need to drag and drop. That you do it together, maybe that one person shares their screen, but that everyone tries something in a notebook, because with this one it might be really helpful to get each other's help to do this, because this will be definitely more difficult than the things we discussed yesterday.
okay.
Yeah, so I uploaded both the CSV and the notebook now in the chat.
Perfect. Okay. You should be able to join the rooms now. Let's see.
And yeah, there are bits of code that I created myself, so I'll try to explain what I'm doing there. And again, this notebook with exercise with the answers will be uploaded at the end of the day, so that you can also try it yourself. So I don't want to dive very detailed in all the data loading bits, but one important step I saw one group struggle with a little bit is that if you miss executing this cell, you will have missing values in your data, and then your machine learning algorithm will actually fail because it cannot deal with missing values. That's why before you do machine learning, you should always do data pre-processing and making sure data is correct. I know it was one of the answers, the questions of yesterday, how to handle missing data. I think I sent the answers to Marta, so I'm not sure how those will be shared in the end. But there are basically three approaches: is just remove the data. That can be done by, for example, doing df df, your data frame drop NA, basically means drop any row containing missing values. Certain cases it might work if you have a lot of data. Certain cases it might not work because you only have 100 data points. Then it's you don't want to do that. So in those cases, you might want to, as we call that, imputing or filling in constant values. Just try to come up with a good guess of the value. In this case, we derive basically the mean of a feature based on whether it's potable, yes or no. So for example, here we check the pH value. If there's a missing pH value, we fill it with the mean. So we if it's potable, then we fill in the mean of the pH value there. If it's not potable, we use the mean of the observations that are not potable. And we do it for 3 observations, just to let you know that these are also important steps typically in before you start doing machine learning. Here again, I use my features as everything except potability. And for Y, my target, I use potability. And then in this case, I started doing fitting on a train test split, but I don't want to discuss that because that is something we did yesterday. One easy way to assess model qualities here, and that's why I did this first, is just use the confusion matrix method of sklearn. So it will give you a confusion matrix with just inputting the actual labels and the predicted labels. But we'll also discuss that later on, because I think most time I want to spend about how to do cross-validation. In this answer slide, I really used
David,
the easiest way to do it, which is just cross-validate. This method is just a built-in method for you to, in one go, do a cross-validation. So maybe I can just show you what it should have been. Sorry about that. I can try at least to do it together. So the first thing you need to do is use the k-fold of scikit-learn. So let me just check this. So if I do k-fold, then there is some kind of hints that I want to use. Here you can see this is a k-fold.
Should I share the data, the code that we wrote in our
No, I
group?
think I can create it on the fly. So,
Yeah,
but let's see. It's kind of a little bit tricky, but I think I can do a live coding session here. So, so this k-fold thing is like a standard class for me that splits my data indices into batches. And so in this case, I already said we want to use probably cross-validation of 10, and I want to do a random state so that it's every time the same. So I just fill in something random, and then I can just show you what this is doing. So, setting a random state has no effect since shuffle is false. Okay, no, shuffle is true. Okay, this is a little bit too much print statement, but you can see what is happening here is that at each part of the for loop, I get a subset of my data indices. What does that mean? I can actually show you that in this cell. So if I want to, for example, just get rows 1 and 2 of my feature data set, I use this ilog method to get those. And I need to provide a list of row indices I want to look at. This k-fold gives me a list of indices that should be used as train. So what I just could do is say I want to use train index. And that one will give me now my training feed, my data set for features for training. So what I can do here at the start of this bit of code is say, I want to define my X train as all the rows that are in my train index. Then I need to do the same thing for my Y train because I also need to say exactly the same labels. So this bit, I create my X train and Y train.
indentation has a problem.
Then I think it's 4 now. Yeah. So next step would be I want to fit my model. So my model is in this case a decision tree. I just fit the most basic one, just for sake of time, and I provide my training data. And just to show you something, training accuracy is basically model.score of X train. So I just want to see the training score of my model, and I can do that using the score function on my train model. So I hope I see something is going wrong. Oh, I said fix, should be fit. Okay, yeah, for the score, I also, of course, need to provide the labels. So you can see at each step, I now get a training accuracy. And of course, I get 10 training accuracy because I use a 10-fold cross-validation. So I will repeat the training process 10 times. Of course, I already said just looking at the training accuracy is not good enough. So what we want to do is we also want to get our test score at each for loop iteration. And then I use my test index that was provided by the k-fold bit here. So if I'm basically repeating the same bit of code, I log, but then with the test index, and then I don't need to train anymore because I already did that. So what I could now do is do print the test accuracy. I do that by model.score x test, and Y test. And let me just, to easily identify which belong together, I just print some random stuff in between. So now you get a feeling. At each step, I now see the training accuracy is 1, which is very high. But then my test accuracy is only 0.75, which actually shows us that we're likely that we are actually overfitting because training is too good and testing is not as good as that. So what we might want to do in another step is change the hyperparameters on the model. I don't want to do that for now because otherwise I'm taking up too much time with the live coding. So the next step you would want to do here, because I said you want to take averages instead of just printing everything. So what we do now is we create a list of scores. So for training and for testing. And we make sure that if we score it, instead of printing it, we add it to our list of scores. And that we can do with this append method. The same holds for this training score. We can do it training scores dot append training scores. So when I execute it now one more time, nothing will be printed, but I will end up with a list of training scores, which will only be a list, I think, which we have already seen. I don't know why it's a little bit slow. So you can see now I get these, which is nice. So the last step is basically to say, I want to have an average. I hope this is the correct command. So for averaging, you typically use NumPy, which has a lot of these kind of mathematical functions for you. So you can calculate the mean and test mean. And when you're a little bit more into the statistics, you know, just looking at the mean is probably not going to do it. So we also want to look at the standard deviation because these two together gives us more insight in the distribution of our scores. You see, in this case, I have 0 standard deviation because everything is ones. And we can do the same for our test scores. Again, we now get an average accuracy. Again, you can see that the mean of the test set and the mean of the training set. Oh, sorry, this should have been, of course, training. Are too different, which means that we probably want to tweak a little bit our model. So what I could do, for example, just to show you something, is I could say max depth is 3. I have no clue what is going to happen to our model. Now, what you see is that the test score, the training scores go down, and they are now very similar to our test score. So training and testing is now the same, which can mean two things. One is we're underfitting or we are fine, and this is just the best we can get. But max depth of 3, I think if you made the plot, you will probably see that could be a little bit too simple model. So maybe in that case, you want to do something like maximum depth of, I don't know, 5, or let's do 6. Not sure what's going to happen here. But you see the training and testing scores both went up, but still we don't have a training at 1. So this is basically how you can do k-fold cross-validation yourself. The nice thing is also what you could do, which is a lot easier, is just use what Python provides you, and that is this cross-validate function. But in this case, what you do is you just supply the estimator, which is in this case our decision tree classifier, and you provide your data and how many cross validations you want to do. So in this case, we want to do 10. Let me just get rid of this. And let's see if this decision tree classifier is not defined. I don't know why, but I made a small typo. And I probably need to do it like this. So you can see, basically, this one line of code is doing all these lines in one go. So what you will see, you will get a list of score. Oh, this is score time. So you will get a list of test scores, which is exactly the thing we also did here. But with a lot less coding and a lot less risk of making mistakes. I hope this is clear, because I think I just want to give you also more practice time. So I'm just going to check if there were some questions. What is the training score? Can you, so just in general, what does a training score mean? Is that the question?
Sorry, yes, I found it in documentation in the meantime, but.
Okay, yeah, so just for everyone, the training score just gives you a feeling of the quality of fit. That's the first thing we discussed today. So then it just gives you an idea, how well can I fit my model on the training set? So the closer this one would go to 1, the better I can model my training data. So typically you would do both. You want to, both. So you want to know how good is my training fit and how good is my test fit. But in the end, the test is typically something that's more important. And then I see, so when we use cross-validation, should we skip the part where there's split data into training and testing? Yes, exactly. So training and testing, which we did, let me just see here, is a separate approach. So this is really the validation set approach. You should never use this during cross-validation, because this does not guarantee that each data point will be used exactly once as a test in the test set. In the k-fold, you will know that each data point is exactly used once in the test set. So there's really 2 separate approaches. So you either use the train test splits, or you use k-fold cross-validation.
David, I want to tell you something. I mean, after we finished, we wanted to validate the what's called the confusion matrix. So what I did is I added the predicted portability into the data frames, and then made a function that check if portability and the check the values of portability and predicted portability, and make decision if it is false positive or false negative, and then I grouped by that. Does that make any sense?
So if you want to do something like that, I think the best practice is to do something. Let me show you how I would do that.
Okay.
Because now I use the model.score, which uses accuracy. But if I want to do a different one, what I could do is just say, let me recall. Let me just give me 1 second. I need to find the method. I have them imported at the top. So for example, you can also do recall. So instead of then calculating the recall, what you could do is determine the confusion matrix and then manually calculate everything. That is probably the one that is nice for the exercise. But in general, you just want to use the built-in recall score. And then instead of doing a score here, you first need to do a predict. So you do a predict here. So you get y predicted. Y test predicted. Let's be very specific here. So you get the predictions of your test set, and then you can get your score. And the score in the end, we want to add to test scores dot append with this. Again, I think it's like you need to provide y test and then y test predicted. Oh, sorry. You can see in this case, the recall you derive from the confusion matrix. So this function is doing that for you. So instead of now calculating the accuracy, I get a list of recalls, and then I can calculate the average recall. That's how I would probably do it. One other way you could do it is, I think, use a cross, I think it's called cross validate predict. What this will be doing is generate predictions based on cross validation. Let me just, it's basically the same way of predictions, come on. Basically the same way of, let me see, I think I should have included it somewhere here. Cross-fall predicts, okay, sorry, this is slightly different. Cross-fall predict. I hope it is working now. So what I get is, I get a prediction for each observation in my data set. So what I now can do is call confusion matrix of, I think I probably need to do y comma this. So now you can get your confusion matrix using crossfall predict, because crossfall predict will give you a label for each of your observations, and then you can actually, and each label is generated when that specific observation was in the test set. So not in the training set, it's really the label generated when it was in the test set. And then you can basically add everything to one large confusion matrix, and you can also try to get some recalls. I think they will be very similar than what you will do when you calculate them in each fold, and then average will be very similar, but there will be some slight numerical changes. But this is also one way you can get predictions using cross-validation. Hope that this is a nice thing that to show. Okay, I see we have 45 minutes left for the course, so I want to start looking at the last bit of theory for today, and it will not be a lot. But this is probably one of the most interesting
I have a
algorithms of
question.
today. Yeah, let's say one more question. Yeah.
Okay, you have a large data set and you want to determine the best trade performance model which you can use for trade, and you have two models, the decision tree and random forest.
Mm-hmm.
Now which one can you go for that kind of for you to determine that trade-off performance, high trade-off performance?
So you want to know when you want to use decision tree and random forest, you mean, or?
Yeah. Which one can you go for? Either two now. Which one can you go for?
You can use both.
If you have a large.
So the idea is that you can train any kind of classifier, and then you can start comparing the performance of the classifiers and pick one. So I would always recommend to test a lot of different algorithms and check which one is working best for your situation. Yeah.
Oh, okay. Yeah, that's right.
All right. Let's discuss the random forest, because those are very powerful methods, and they're actually just a small extension on the decision trees we have been discussing today. So in the last bit of theory, we will cover ensemble methods, and ensemble methods come in the form of bagging and boosting, and also in general just the ensemble. So what are ensemble methods? The idea of an ensemble method is not that it's in general a new algorithm. What it is trying to do is combine multiple models or multiple algorithms that are on its own pretty weak, but when you combine them, they are strong. So the idea is that an ensemble method consists of multiple models, and that will make sure you get in the end a stronger learner, because more predictions in the end, and if you average them, for example, give a better feeling of what it could estimate of what it could actually be. So that's the idea here of the ensemble learner here, is that you can pick any kind of model you want, and you will train them on the same training set. Those will give you a trained model, and then you combine all the models together by making a prediction. So for example, if you want to make a new prediction for an observation, you will call all your models. All models will generate a prediction separately. So in this case, we will get 4 predictions, and then you want to combine them using some kind of aggregator. In this case, it could be a mean when you're doing, for example, regression. And this mean then is in the end used as the actual prediction for the model. So you see, really, you can actually, this is KNN, means K nearest neighbors, linear regression. You have a decision tree. This is something we won't discuss. This is a support vector machine, I think. All these different things, you can just basically combine, and typically these models are stronger than each of these models separately. This is, so in the end, you will be less prone to overfitting, because maybe one is overfitting but the other not, and they balance each other out. You have a lower error because you have that's the idea of this whole aggregation. And it says here it tastes great, in the sense that what I also typically find is in machine learning project, when you're exploring which algorithm you want to use, you're fitting already multiple models yourself. So why not just combine them in the end? Of course, the downside here, you definitely have downsides because there is more expensive than just to train one separate. But also it becomes not so easy to explain anymore because you have multiple models making predictions and then in the end combining them. So the interpretability of these models go down. So this is one way to do ensemble learning. So if you're interested, there's a very nice video explaining this. Another one is called bagging. Bagging is actually just a technique to reduce variance of predictions by combining, again, multiple classifiers. But the key here is that we use different subsamples to train each of these classifiers. So bagging is actually just a smaller version of bootstrap aggregating. So how does bagging work? What we so what we do is if we want to train n different models that we in the end want to combine together as an ensemble, what we do is for each of these separate models, we only consider a subset of the data. So we randomly pick, and in this case, we randomly pick with replacement, meaning that you can pick the same observation multiple times. So you randomly pick maybe 5. That's at least the example we have here. You pick 5 data points from the data set. And then for the next model, again, you pick 5. And you do this basically for every model. So you get a subset of the data for each model. Then the next step would be to train the classify on each of these subsets of data a new classifier. And finally, you combine each of these classifiers again with probably something like a mean or a mode or whatever works best for your specific use case. One very well-known example of a bootstrap aggregating is actually random forest, because what random forest is actually just doing is you have your input data, it does the subset with random replacement, and then each of these models is actually just a decision tree. So instead of just considering one decision tree, you're considering multiple decision trees together. And these two decision trees together, then when you aggregate them or something, or take a mean, give you a prediction. So as you can see, it's actually not really a new algorithm on its own, because it's just leveraging everything we already learned from decision trees. So when you're doing, for example, a classification problem, and each of these trees is giving, let's say, a label, you can come to one final prediction using, for example, just majority voting. So again, in the example of having New York and I was going to say Las Vegas, but we're taking San Francisco. If you have more votes for San Francisco, then that will be the one that you predict. So this is something that works very well. This is a very easy method to just implement, and it's just a slight extension on what we have already known. So again, you can also use the same hyperparameters that you have seen on decision tree to make sure that each of these trees don't overfit. But the whole idea of these ensemble methods is that it also should not be as important to figure out what hyperparameters are best to use, because at each of these things you're only considering a subset, and you might be training 1,000 of these decision trees, which means that you're actually less likely to suffer overfitting. Then lastly, you could also do boosting, and boosting is just a slight deviation to bagging, because with bagging we have all these data sets that are independent of each other, because we construct them using random drawing with replacement. So each of these things are independent, meaning that we can also calculate everything here in parallel. With boosting, we're going to try to build complementary learners, meaning that if the first model that we train is performing bad on specific observations, we want to try to get a second model that's doing better in the places where the first one is doing worse. So just to show you here, what we do first is we draw this first data set, in this case just random, and I don't think also not with replacement for this one specifically. So we get again our first subset and we train our model. Then we test it. And then we find out which observations are not not well predicted. Then these are given a separate weight, such that in the next iteration here, the subset D2 is more likely to pick up on the observations the first model was performing worse on. So you can see these orange dots here are now actually already 3 are present in this second subset. And then again, you retrain your model and then you try to see the performance of this whole ensemble. And then you again see this ensemble is performing worse on these observations, then give those more weight. And then in the third data set, you're more likely to draw again the observations that were not well predicted, and so on and so on. So this one is trying to really get complementary learners, and you could look at it from this perspective. So for example, here you can see the first learner learned to only predict the 2 pluses here very well. So here in this case, you're classifying pluses and minuses. So these 2 are well predicted, but the rest not. So in the next iteration, you see this minus, these 3 pluses were given additional weight. So the second model is actually now predicting these 3 pluses correctly, but still it's not performing well on these 3 minuses. So in the third model, that one learned that how to predict these 3 minuses correctly. The nice thing is with these simple decision boundaries, if you would combine them together, you get now a perfect model, because with the 3 decision boundaries together, you can classify each observation correctly. And that is essentially what you're trying to do with boosting. And one well-known algorithm for boosting is called ABW, which stands for adaptive boosting. So you can also use it in scikit-learn. So what did we learn in this last bit of theory? That when we combine multiple weak learners, we get actually a stronger model. But that also means the complexity of the model increases, meaning the interpretability goes down. One famous example is really random forest, and I would highly recommend in the last bit of this course to play around with the random forest. And of course, because they are more complex, they are in general more accurate than just a single decision tree, for example. So yeah, these are the packages you can use, but I think I already imported it for you in the project, and that was the last bit of theory. So I would recommend, because we only have half an hour left, to go right away to the exercises again. And I see one question: can you push this notebook to the repository? I will do that, but only after the course again, because I will try to reserve 10 minutes to close, so we only have 20 minutes left for you to play around with random forest and other things you want to do. So let's go to the breakout rooms again.
Yeah, I will open it. So then we will be back at 10 minutes to 6.
Yes,
Okay.
please. So I hope you all enjoyed. Oh, sorry, I think a lot of people are still coming in. I hope you all enjoyed the freedom you have in this exercise. It might also be daunting because you don't know where to start and where to go. But I hope you also see that that's also a nice way to explore the things you find interesting. For the last bit of this course, I want to just show you the notebook I built. And this is something I will upload in the end so that you can check it for yourself. So I built here a function that can do cross-validation for multiple estimators that I give. So in this case, I have, I think, do I have multiple? Yeah, so I have two different decision trees. So I have just a default decision tree, and I have a decision tree with some hyperparameter set. And then this function is in a for loop doing k-fold cross-validation for both of these classifiers. So you can see, I think in the end, these classifiers are in accuracy pretty similar, but you can see that the precision and the recall changes. So in this case, you need to check with your context or your client which would be better. And now, of course, the question is, can we plot this on a ROC curve? Because that's one bit I think no one covered during the exercise, and it's also probably the most advanced bit we did. So that's why I built this code for you that calculates the ROC curve, which is this. For these decision trees, it's slightly different because you can see it's not a continuous line, which you might expect. And that is because of a specific reason. So it's the most easy to explain this with this orange point. You can see this is basically the default classifier. And there's just one data point on the ROC curve. And what happens here is that this decision tree, because I did not specify any hyperparameters, is going to grow to have one observation per leaf, meaning that I just always get the same kind of prediction. Sorry, predictions for my how do you say that? I just know. What happens then is that I will always have either 100% prediction probability or 0% prediction probability, because that one observation that I leave is either of label yes it is potable or no it is not potable. So prediction probabilities are always 0 or 100. So it doesn't really matter what I do with my decision boundary. If I set it at 50%, I get the same labels because yeah, the 0 and 100 are not in that range. So in this case, it doesn't matter where you set your decision boundary, the results are always the same. And that's why this is just represented with a dot. So here's a little bit more variation in prediction probabilities, but again, I think a lot of prediction probabilities will become either 100 or 0, meaning you don't get this continuous line. So it's a little bit harder to interpret these overfitted models on an ROC curve. But yeah, let's just continue. So this is code to explore the decision trees, and I don't want to do that. So what you could also do is just fit logistic regression and then also plot it on the ROC curve. So you can see this one gives you a nice continuous line, but apparently this model is not well suited for this use case because it's basically not doing better than a coin flip. Then you want to go to random forest. So for the random forest, I have the default one and a tweaked one. So I changed the number of estimators to 250 and changed some hyperparameters. So just to show you that these are less prone to overfitting, you can check the cross-validation results. So yeah, the downside here is that one of these classifiers takes a very long time to calculate because of course you need to fit 250 estimators. So you can see this one is now generating 0.77 in accuracy and pretty okay with the precisions. And I think these are definitely better than the decision trees we have fitted. So unfortunately, this takes a very long time to execute. There they are. So you can see we get a slight boost in test accuracy, but they're very minor. So even if I try to get all these sub decision trees not to overfit, in the end, I get very similar results for both the default random forest classifier and let's say maybe an optimized random forest classifier. And then, of course, what you also can do is try to fit both these classifiers in the ROC curve that we generated before. So here you can see these give you this nice continuous lines, because now with so much decision trees, the results will be not just 100% and 0. And then you can see the random forest classifiers are outperforming both decision trees and definitely the linear logistic regression one. And you can see it really doesn't matter if you would pick the red or the purple one. Also, if you look here, I calculated the area under the curve. And you can see for both random forest classifiers, they are very similar. So yeah, it doesn't really matter in this case.
Sorry, David, I don't understand the graph actually. Forgive
Okay.
my stupidity about it.
No, just to recap, because maybe that was indeed a bit of theory that might already faded away. So the graph here is related to the confusion matrix. So you have the true positive rate on the y-axis and the false positive rate on the x-axis. I don't recall by heart what those are actually again. So I think true positive rate is the same as the recall, meaning how many did I correctly classify as positive out of all the positives, right?
Okay.
And then the false positive, I think, is basically out of all the positives, how many did I classify in? Sorry, I don't think that's correct. And let me just check. Sorry, I always forget.
How many did you classify as positive and they are actually negative?
Yeah, I think that's indeed the case. So I think false positives are how many did I classify correctly out of everything that should have been negative. I think that's this rate. So you plot these two rates, and this gives you a good curve to compare classifiers. So the closer they grow to the upper right, upper left corner, the better they are. And that's why the random forest classifiers are better. And just to boil this down to a number, you can calculate the area under the curve. So you just integrate basically, and this gives you the area under the curve. So the higher it is, the closer to 1. And that's why you can see, so I can't calculate the area under the curve for the decision trees because they are just discrete points. But for the continuous lines, I can calculate it, and you can see the logistic regression is just 0.5, just slightly better than a random coin flip. And you can see that the random forest classifiers are better. And in the meantime, just to complete the whole, that you can see everything together in one go, I also did an adaptive boosting. Again, adaptive boosting also uses decision trees. And then I trained 2 different adaptive boost classifiers, one default and one slightly tweaked. And
Actually,
you can also see it
for
in
all
the
of them, the decision and the logistic regression and the decision tree, all of them are almost 50%.
Yeah, so that
right?
you always plot the same model. So this is just that one logistic regression model I fitted a couple of cells before. So you can see now the adaptive boosting in yellow and the other adaptive boosting in gray are not performing better than the random forest. So in this case, I would say probably better to use a random forest classifier for this use case. Yeah, that concludes this this notebook exercise, but also the course. And because I see we are exactly at 6 o'clock.
Thank you very much.
Yeah, I want to thank you for your participation. I really enjoyed it. You asked a lot of very interesting questions, so I really thank you for asking them because that makes it interesting for me. And yeah, I hope you learned something and that hopefully you can also apply it. And maybe I will see some of you in the projects because I will also be a mentor of certain of those projects. So
can I select you as a mentor?
Not sure if it works that way. Yeah, have a lot of fun with the remaining part of all the this year's courses, and I hope to see you somewhere else. Have a nice day.
Thank you very much, David. Thank you for your time, and thank you everyone for participating.
Bye.
Bye.
Yes.
Bye bye.
Thank you. Thank you. Bye bye.
Thank you. Thank you.
Thank you,
Bye.
David. Thank you.
Thank you,
Bit
David.
challenging, but okay.